So let us discuss these. The first one is like we have to show a relationship between 2 points P0 and P and a vector which joins these 2 points and a vector which is normal to that plane. So we are in between option C and D. Okay, because we know very well that dot product of these two vectors, because these are orthogonal to each other, is going to be 0. So it is either it is 0 as a scalar or as a vector. So which one is correct, C or D? C, because dot product is always
Scalar quantity.
Scalar quantity. So this one is correct. What about this?
Graph में orthogonality show the
No. If the cross product is 0, the vectors are parallel. If the cross product is 0, like in this case, but this relation is true. Not in this case, in general, because the cross product is always a vector quantity. And if the cross product is 0, the vectors are parallel. But these are not parallel. What about this one? We have to show that what is the distance between the origin. So let me draw it. This is origin. And the point where the xy plane intersects this line. So this is xy plane, let's say. And there's a line which comes and intersects this xy plane at this point. Now we have to find out the distance between this point and this origin. And we know very well what is the distance formula in 3D case. The same is square root x2 minus x1 square, y2 minus y1 and z2 minus z1. But we know very well what is this point. This point is origin 0, 0, 0. What is this point? That's a question. If you got this point, we are done. So there is one point here that you should keep in your mind. This line intersects xy plane.
So Z.
Yes. So in xy plane, we know very well the value of z is always 0. So we are done. Simply you have to take this z 0, and from here you will get the value of t to be 2, and put here that value. The value of y is going to be 8, and the value of x is going to be 6. 6, 8, and 0. 6, 8, 0 is the point. Now you have this point, you have this point. Apply distance formula. So that is
36.
x2 minus x1 square plus y2 minus y1 squared plus z2 minus z1 squared. But this z1, y1 and x1 are 0 because it's origin. Simply you put these values, square these, sum them and take the square root. We are done. So that's going to be 10. And units, whether that is meter or something else.
Unit.
It's a unit. Okay, how about this?
A
This is a circle.
A after C. So radius same हो तो
Yes. Which one of these equations define a circle?
radius भी same हो जी.
If the radius is same, then it's
तो
going to
height
be a circle.
fix हो जोड़ी.
Height.
variate कर दी तो
Yes.
वो helix वगैरह थी वो.
Yes. The first thing is that we have to look at these two options.
It can be point circle.
Whatever. But first we have to look at these two options. But these two are unfortunately wrong options. Because whenever the last component is 0, it means we are in xy plane. Now what is the problem with these two? You can see this coefficient is 3 and this one is 4.
Radius is not same.
Yes, so this does not define a circle, but this defines an ellipse.
Ellipse type.
This is not a circle. So simply it has been cancelled. And again this is 3, this is 4, this defines an ellipse. This is not okay. Now check the last component. This one is 40 and this one is 40. There is a parameter t. It means we will go upside in the direction of z. So we are not in a particular plane, so it can't be a circle. It is not possible that this thing is going to be a circle
Family of circle.
or this thing is going to be a circle. But we are okay with this option. What is the reason? It is not necessary that our circle must lie in xy plane. It can lie anywhere. So this circle lies when the value of z is 4. So 0, 1, 2, 3 and let's say
It hides
4. So the circle lies here where the value of z is 4 and the radius of circle is 3. What does this mean? When the coefficient of angle is 2t, it is not t, it is 2t. So if I am going to change this particular thing with t, then what happens? And if it is 2t, what happens then? If it is 3t, then what happens?
Size में control होना चाहिए ना बाकी angle.
No, size would be same because size is defined by a radius. We know very well. This is radius and this is the height where the circle lies. What does this thing tell? It will affect the particle that moves along that circle.
Space में
It will affect its velocity.
अच्छा.
It will affect its acceleration. Because what happens when this t is only t, not 2t, then you are going to complete
Slow.
a rotation in, let's say, 10 seconds. Then you will, if this is 2t, then you will complete the rotation in 5 seconds, and in 10 seconds you will complete 2 rotations. And what does it mean? That the velocity of the particle is different and the acceleration of the particle is different when that is the case. Because we know very well the velocity is simply the derivative of this one, and when you differentiate, the derivative of this thing is going to be multiplied. So this 3 becomes 6. And when you differentiate again, it becomes acceleration. Then you again differentiate and this 2 gets multiplied, it becomes a higher quantity. How about this case? I think it's very simple.
So in 3D we have also circle. That's the interesting case actually.
Yes, yes. Because we discussed that thing yesterday that these are called 3D curves. The curves that lie in 3D. Okay, what about this?
14, sir.
Acceleration
8 times
8 times 0. So what do? You just differentiate this quantity
Twice.
2 times
Twice, yes, sir.
and put the value of t to be 0. I want this. So this is not a scalar. This is a vector quantity. So there should be I hat and there should be j hat. It's not only a number. Okay, so what is that going to be? So our prime of t would be, I am simply finding out the second derivative. So that's going to be
the 8.
2 times 2, 4, 4 times 2, 8, I hat
Yes, sir.
plus 60
60 and 60.
and then 6 j hat.
Yes, sir.
And at t equals 0, this becomes
8 I plus 6.
8 I hat
Yes, sir.
plus 6 j hat.
Yes, sir.
So this is the acceleration. How about this? You differentiate with respect to x first, then you differentiate with respect to y partially, and put this point, you are done. So we have these type of basic questions in some of the tests. We have other questions as well related to multivariate calculus.
Sir, I'm talking about option number B. What is called the equation of ellipse, sir? Because the both values are changed.
Yes, this is 3, this is 4. You know very well this is x is equal to 3 cos 2t and y is equal to 4 and sine 2t. You just take 3 here and you just take 4 here. This becomes cos 2t sine 2t. You square it, you will get this equation. I think x square by 9
Right.
plus y square by 16, which is equal to 1, which is an equation of ellipse. We know very well. But this is going to be the parametric form of that. Okay, so I think we should discuss multivariate first, complete it, and then we are moving ahead towards real analysis. So we left at, I think, multivariate limits and differentiability. What is the chain rule in multivariate case? Of this, there are still some of the questions, but the topics we have not discussed yet. Let us discuss those, then we are going to discuss those MCQs as well.
Sure.
So We have a function, let's say w, that depends upon x and y, and x itself depends upon t, and y itself depends upon t. We are interested in this thing, the derivative of w with respect to t. So what is the rule for that?
Partial f over partial x, partial x over partial t.
Yes. So we call this particular thing to be chain rule.
Yes.
We have chain rule in single variable calculus. Now this is what we call the multivariate chain rule. So I call it what we say.
Chain rule.
Let me write this thing. Track 1, and this is going to be lecture 2 because we are going to continue from the yesterday. So this is chain rule. Now what is there basically? W depends upon x and y.
Yes.
So whenever a function depends upon two independent variables, then you always define a partial derivative. I cannot say this is going to be dw by dx, but it will always be partial w by partial x. Why? Because this w depends upon more than one variables.
Several.
Yes, but what is the good thing? That x and y both does not depend independently upon two different variables, but they depend upon a single variable t. So what you can define here, you can define partial w by partial y and partial w by partial x. But since x and y both depend upon a single variable, it's only t, then you can define here dy by dt. It will not be partial y by partial t. What is the reason? Because y only depends upon a single variable. And here you cannot define partial x by partial t, because x only depends upon a single variable. So this is dx by dt. But you need this thing, you need the derivative of w with respect to t. So from here to here, how can you reach?
In two ways.
You have two directions or two ways. So the first one is you take this direction. Then your this derivative would be partial w by partial x multiplied by dx by dt, plus then you take this way, that is partial w by partial y times dy by dt, and this is what we call the derivative of w with respect to t. How about I write this thing as this, partial w by partial t. Is it okay or not? Why I wrote dw by dt rather than partial w by partial t? Because what I say, w is a function of two variables. Let's say x square y cube plus y square. W depends upon how many variables? Two. That is x and y. So that I can define partial w by partial x and partial w by partial y. Now x depends upon a single variable, that's t. Let's say t plus 1. And y depends on a single variable, that is t square. When you put these here, w becomes only
Function of
a function of t. When you put the value of x and when you put the value of y, w becomes only a function of a single variable, that's t. That's why you can define this thing, and this is not okay. This is not okay. The reason is you can only define one thing. So if I ask you what is the value of dw by dt, how will you do it? Just apply this formula, or first you put the value of x and y here, then simply use the derivative in the case of single variable. So it depends upon you. Okay, so there is a chain, you are moving from w to t by using this way and this way, that's why it is called chain rule. Because you are making a chain to connect the things. Okay, so
First we will say that the value for x and y.
yes,
Directly they will.
first substitute the value of x and y here, then find this thing. That's going to be dw by dt.
So can we say that dw by dt is the total differential of the w function?
We can say, but it is somehow another concept as well. We can call it total differential as well. But differential is something that is dw. It is not with respect to t or with respect to z. When you define a differential, it's simply the change in a particular function. How about some other directions in this particular case?
When function is more than 2 even?
Yes. So we have a function w that depends upon x, y and z. It means 3 variables. And x, y and z itself depends upon 2 variables, let's say u and v. It means you have the value of x in terms of u and v. You have value of y in terms of u and v. You have value of z in terms of u and v. When you put these all the things in this particular formula, then w depends upon 2 variables. One is u, other is v. Now what can you define? Either you can define partial w by partial u. Now you cannot define dw by du. Because finally w depends upon 2 variables. One is u, another is v. And you can also define partial w by partial v. But how can you define this particular thing? There is simply a chain rule that can help you to do this. So let us make a diagram. W depends upon 3 things: x, y and z. And x depends upon
2.
u and v. Y depends upon u and v. And z depends upon u and v. So this is a diagram. Or you can write u and v once and you can connect these with different lines. But it will be a bit messy. We can do this. W depends upon x, y and z. And x, y, z both depend upon u and v, u and v, and u and v. So this is another diagram. Now you need what? You need partial w by partial u. So what you have to do, you have to start from w and you have to reach at u. How many directions do you have?
3.
You have 3 different ways. Like you take this way, then you take this way. You cannot take this way because this leads to v. Then this way, and this way, and then this way. So simply you take this derivative, you take this derivative, you take this derivative, and add these 3 quantities. That's going to be partial w by partial u. So what is going to be this direction? This would be partial w by partial w by partial x. And this would be partial x by partial u. So partial w by partial x by partial u in product. Now this is partial w by partial y and partial y by partial u. And simply this would be partial w by partial z and partial z by partial u. What happens in this case?
U replaced by v.
Yes, if you want partial w by partial v, then what happens? You take this way, then you take this way because you have to reach at v. You take this way, then this one because you have to reach again at v. This way and then this way. So what happens in this formula? Only
V changes, U changes.
this u changes into v, this u changes into v, and this u changes into v. So this is going to be partial w by partial v. So we might have lots of examples in this case. For example, I am taking a function w that depends upon x, y and z, and let me define it in this way: x, y square times z. And what is the value of x, what is the value of y, and what is the value of c? This is, let's say, u, this is v, and this is u times v. Now x depends upon u and v. It is not necessarily that both terms must be here.
0 is there.
It's not necessary. It could be v power 0. And this depends upon v and this depends upon u and v. Now, what you can do, you can put the value of x here, you can put the value of y here, you can put the value of z here, then you can find out partial w by partial u or partial w by partial v. Then this long formula is not okay. Then you have to simply apply the short formula, that is simply partially differentiated. But why this is a good formula? Because when these terms are a bit messy, there are logs and exponential functions and trigonometric functions are there, then these calculations become very difficult. Now we are applying both methods to find out whether our answer is okay or not. So let us check that. I want partial w by partial u. So what should I do? I want the value of partial w by partial x. It means differentiate this thing partially with respect to x. The derivative of x is going to be 1. So we have only y squared times the derivative of this thing is going to be 0.
Yes, sir.
Because we are differentiating partially with respect to x. Then, okay, let us deal with these things. Partial with respect to y.
2x.
That's going to be 2xy times, then partially with respect to z. That's going to be 1. Now, partial of x with respect to u, then partial of y with respect to u, partial of z with respect to u. Partial of x with respect to u is 1 times 1. Partial of y with respect to u is 0. And partial of z with respect to u is v. Then this becomes y square plus this is 0 and this is v. Now this contains y and v. Either you have to convert these into y, x, y and z, or you have to convert these x into u and v. So y is there, put the value of y. What is that? V. So that becomes v square plus v. So this is what we call partial w by partial u. How about another way? What we can do there? Put these values here. Put these values here, then differentiate. So what happens? What is the value of x? U. What is the value of y? V. So u times v square plus the value of z is uv. Now w only depends upon two variables u and v. So partial w by partial u would be u.
V square.
V square because derivative of u is 1, derivative of u is 1.
Plus v.
That's same as that. V square plus v square plus v. But it is not always possible to put these values and differentiate, or it might be possible but difficult. So we should know this way as well as that one. But this thing is not that, okay, memorize this formula. It is not that thing. I just made this diagram to explain you how you can do these things. Now my question is, why did I not write here dx by du in the previous case?
Now x is the function of several variables.
Yes.
So x depend upon 2 u and v.
If x, y and z they independently depend upon a single parameter t, then it would be dx by dt, dy by dt, dz by dt. But in this case, x, y and z depends upon more than one independent variable. And just keep this chain in your mind and you can make any formula in which you are supposed to find out the partial derivative of any function with respect to any given variable. Okay, any question from this? I think this thing only makes good when you do a lot of practice. Okay, and there is lot of practice available in calculus books as well as on internet. You take calculus book by SM Yusuf, you will be getting like not hundreds but 40 to 50 questions only on partial derivatives. But when you take any calculus book, you will get hundreds of questions on partial derivatives, but they will be involving chain rule as well. Okay, so as promised yesterday, we defined what is partial of a function with respect to x. It means in the direction of x. And we defined what is a partial of a function with respect to y. It means in the direction of y. Now we are going to define a generalized derivative. Not generalized derivative, but derivative in a generalized direction. It means in any direction. What we call it?
Directional
Derivative. And one good thing is that directional derivative must lead you to the partial derivatives in the direction of x and in the direction of y. So let us do it. So given a function f of x comma y, and we are given a vector u with components, let's say u1 and u2, but we claim one thing, that the magnitude of this vector is 1. We'll be discussing why it is necessary later on, that why the vector that we have taken so far and we want the derivative of that function in this direction, why the magnitude of this vector is 1 and why it is necessary. Okay, so what we need to find out the derivative of this function. Now I'm not writing partial f by partial x because we are discussing some sort of generalized derivative. In the direction of u at a particular point, let's say x naught, y naught. Okay, so our vector has two components, u1 and u2. u1 is a scalar, u2 scalar, because components are scalars and the vector itself is a vector. And we have a function. Now what you need to do, you need to partially differentiate f with respect to x, then evaluate at this point x naught, y naught. We know very well what do you mean by this. We can do it. Just multiply this quantity with the first component, u1. What is the first component? This one. Then what you do? Partially differentiate f with respect to y. Evaluate at this point, what we call it x naught, y naught, and multiply it with the second component u2, and just add these things. This is going to be the directional derivative of a function in the direction of a vector u at point x naught, y naught. This is like a simplified version, but we can make it a bit compact. We can make it compact in the case of using the gradient function, del operator. But is it okay? That we know very well what is partial f by partial x. Just find that value, multiply with the first component, plus find this value, multiply with the second component. This is any vector in any direction. Now, what if this vector is 1, 0? Is it the direction parallel to x-axis?
Yes.
This is the direction parallel to x-axis, because the x component is 1 and the y component is 0. So you are moving only in one direction, that is x-axis. If you put this value over there, what will you get? What is the value of u1? 1. What is the value of u2?
0.
This becomes,
Vanish.
what you get?
Partial
Partial f by partial x. So this directional derivative gives you partial derivative in the direction of x when you take this vector. That's why it is called directional derivative. It means you get derivative in any direction. What if you put this thing?
0.
0, 1. What is the direction of this vector? Along y-axis. What is the value of u1? 0. Put it here. This thing becomes 0, and this thing becomes partial f by partial y. That's the derivative in the direction of y. That's why we call it the directional derivative. It means derivative of a function in any direction. Now the thing is that what is the compact form of this? Can I write this whole thing in this way? Partial f by partial x, and let me remove this point for now. I hat plus partial f by partial y, j hat in the vector form, and let me write point x naught, y naught, because I am going to evaluate this at this point, and the vector u1 and u2. If I write this vectorial form, then I think no need to write this. Then the dot product of these. What is the dot product of these two vectors? You know very well, the first component multiplied by first component, that becomes this. The second component multiplied by the second component, and that becomes this. So I can write this thing in. Is it okay? Okay. So we name this quantity to be del f, what we call gradient of f. At any point, let's say the point is x naught, y naught, dotted with the vector u. So this is what we call the compact form for the directional derivative of a function. So you are given a function, find its del, evaluate at point x naught, y naught, and just take its dot product with the unit vector u. So that's what we call the directional derivative. So let us discuss an example. A function that is given to us is 2 minus x square minus y square, and the point at which we need the directional derivative is 1/2 minus 1/2, and the vector u is minus 1 by square root of 2 and 1 by square root of 2. So how to do this? So what we need this thing. First of all, you are given a function, you are supposed to find out its del. And how to find out its del? Partially differentiate with respect to x, partially differentiate with respect to y, and evaluate at this point x naught, y naught. I think there is again one mistake. Comma. Okay, so what is partial f by partial x? That's going to be minus 2x, and partial f by partial y becomes minus 2y. Then del f becomes minus 2x minus 2y, and you evaluate at the point x naught, y naught. What is the point x naught, y naught? So that's the point 1/2 and minus 1/2. Put these values in this one, then you get the value of del f to be 1/2. So this becomes minus 1, and minus 1/2 becomes positive 1. So this is del f at the particular point. What is the vector u? Vector u is minus 1 by square root of 2 and 1 by square root of 2. You just take their dot product. So the directional derivative of the function in the direction of u at the point x naught, y naught becomes minus 1 multiplied by minus 1 upon square root of 2 would be, and this becomes, so this becomes 2 by square root of 2, but I think there is some calculation mistake. This should be 0. If it is there, you may take it. It should be. Yes. Is it somewhere else? 1/2 minus 1.
When you multiply minus 2x with 1 under radical 2, so minus under radical 2 must be the numerator.
Okay, whatever, but the method is clear.
You are
There's a
multiplying with 1 upon 2, and we have to multiply with 1 upon under radical 2. In multiplication we have a problem actually.
This thing?
No. Yes, there.
Yes, 1 upon 2 multiplied by?
No, we have to multiply with 1 upon under radical 2. See the u?
No. This is the point x naught, y
X
naught.
naught, y naught.
Okay.
This is the point x naught, y naught.
Okay.
And this is your vector u.
Vector.
You just find this and you put the value of x naught, y naught here. And then you take the dot product with the vector u.
Okay.
So whatever, but the method is okay. This is the method. So simply a function is given to you, a point is given to you, a vector is given to you. This vector must be a unit vector. It means you find its magnitude, it should be 1. Then take partial f by partial x and partial f by partial y, evaluate at this point, this is your del f. Del f is defined in this way, what we call the gradient of a function. And one thing else, just then take the dot product, you are done. This is what we call the directional derivative of a function in the direction of u.
ग्रेडियंट एंड नेबुला में फर्क होता है ऐसा ये आए चक्कर ये न्यूमेरिकल में
apply a shift operator.
No, in numerical there is a difference. In numerical, but in calculus or PDEs, this is what we call gradient operator or Del operator, and this has a different meaning. This has a different meaning. This is, I think, square to, this is equal to,
x2 minus x1.
no, this thing is called Laplacian operator. When I write this thing, this is called Laplace equation.
Partial 2 or
Partial
x
2u
plus
by
partial
partial
2 or
x2, partial 2u, partial.
harmonic function.
Yes. This is Laplacian. We also write this in this way, I think. Laplacian operator. we write in
Partial
that
dot with partial.
partial dot with partial. But this del square is written in this way. In partial differential equation as well.
Sir,
Yes.
you will show some df upon d, partial differential upon f upon d, you multiply.
Multiply with the first component. This is called what we say the dot product. Multiply the first component with the first component and the second component with the second component. This is what we call the dot product. Okay, the question is why this magnitude should be 1?
This is direction.
Because this vector must give direction. It has nothing to do with the length.
So
If I, okay, you know very well, like 1 comma 0, 2 comma 0, 3 comma 0, they give us the same direction. But when you multiply these things with some higher numbers, they will give you the higher derivative. So the value of the derivative is 2, then the value of the derivative is 4, will be confused. Then what is going to be the actual slope? So the actual slope is when you multiply with a normal vector or unit normal vector. Because when you increase the length of this vector, the slope will be increased. So this will like misguide us and mislead us that okay, this particular function has this type of greater slope. So in simple words, this thing only tells us direction and it has nothing to do with the magnitude. So we are claiming the magnitude of this u vector should be 1. If it is not 1, then we might get different slopes. Okay, now there is a new thing here, what we call del f. What does it tell? What does this particular thing tell us?
change in both directions.
Change in both means
X
when
and Y.
it is dotted with u.
Slope.
This is giving us actually scalar.
Okay, let us do a practice and then we'll get an idea what happens. You know very well, this is a surface that lies in 3D. It is some sort of parabolite. A parabola, and you rotate it, that becomes a parabolite. Now, we know one thing that, what is this?
This is circle.
Family of circles in xy plane, but we know very well that for that surface, this second equation behaves like contours.
Contour.
You have surface and you are going to project every circle down, that is contours. It means this will give us a shape like this. And I ask you, what is going to be the del f in this case?
2x plus.
What is the partial derivative with respect to x?
2x plus
Partial derivative with respect to y?
2y.
2y. Okay, this is del f. And I want to evaluate this del f at a single point. So let me take any point here. Let me claim this value to be 1, 1. Put here 1, 1. What's going to be the result?
2.
I want you to draw this vector at this point. I'm giving you a point, initial point of a vector, and I'm giving you a vector. Then draw this vector at this point. What is the vector? 2, 2. What you will do, you will start from here, you will go 2 units in x direction and 2 units
In my direction.
upward direction. This is your vector. This is your contour or any graph. This is a vector. Is this tangent or something normal to that particular point? So one thing is there. This is the gradient vector which we call del f evaluated at a point. This is always normal to the contour plots. Always normal. The del f is always normal. You can evaluate at some other points as well. Okay, you take this point. I claim this point to be, let's say, 2, 0. Put it here, you will get a vector either in this way or in this direction, but it will always be normal. And what do you mean by normal? This is the tangent, and the vector that is perpendicular to this one is called normal vector or orthogonal vector. So this is always the case. That vector is always orthogonal. We'll use this thing when we are going to study Lagrange multipliers for optimization.
So actually it shows normal vector, and normal vector always has magnitude 1. That's why we are making it in directional derivative. U must be have magnitude 1. So U is actually showing the direction.
Yes, but
so normal vector.
but this thing has no connection with U.
I am
Yes.
For my understanding, making it.
Yes, right. Okay, so next thing is that we'll be using this idea when we are studying Lagrange multipliers. I think after 1 or 2 topics. Any idea about linear approximation,
Curve fitting.
curve fitting?
Y minus y1 equal to mx minus x1. This will give us idea.
Like you have a curve and at a point you want to approximate this with a
Another polynomial.
with a tangent line. And when I call linear approximation, it means whatever function you have, you are going to approximate that with a straight line. You have a function, let's say that is y is equal to f of x, and this is the point, let's say the point is x0, y0. You want to approximate this function with this straight line, so that in the neighborhood of this point, the distance between this straight line and your function should be minimum. It should be minimum in the neighborhood. But when you go far away, the distance might increase, might decrease, depends upon the function itself. So the question is how you find the equation of this straight line. That's very easy. How we do it?
By slope.
Y minus y0. What is y0? This point. Equals m times x minus x0. But what is m here? That is the derivative of f with respect to x evaluated at x0, y0. This is what we call the equation of straight line, or what we call the tangent line to a particular curve at a given point. And in other words, we call it linear approximation. Now we want to extend the same idea to a 3D surface. Like you have a surface that lies in 3D, and you take any point on the surface and you want to approximate this with some sort of plane that is tangent to that surface. You have a surface and you want to approximate with a tangent plane at a particular point that is given to you. So I think the idea would be same. What is this point? x0, y0 and z0. And the idea would be similar to this. This surface is f of x comma y equals
Z.
A surface is this. But you want equation which is tangent to this surface at this point x0, y0 and z0. So the idea is same. Z minus z0, because here the dependent variable is y Here the dependent variable is z.
Partial
Then you have x minus x naught,
y minus
but partial f with partial x, evaluated at
x naught.
x naught, y naught. But there is something else, that is y minus y naught multiplied with partial f partial y, evaluated at x naught,
Y naught.
y naught. This is what we call the linear approximation of a surface that lies in 3D with a tangent plane at a given point. So these are the questions that might appear in some of the tests, and I have seen a few of them. So I give you a surface, I give you a point. I want this thing from you. So how you do it? Maybe I am taking the same function. At the point I am taking is 1/2, and since I only need this thing, yes. So how you get that thing? Is it easy?
Yes.
So just put the values in this one. First, partial f by partial
Minus 2x.
x. This is 0, this becomes 0, this becomes minus 2x. Evaluate at this point, I am writing only p right now. The value of x is 1/2, so this becomes minus 1. Partial f by partial y, that becomes minus 2y. Evaluate at this point becomes minus,
1.
put this value becomes minus 1. Now put the value in this one, partial f by partial x,
Minus 1.
minus 1 times x minus
1 half.
x naught is
1 half.
1/2. This is again minus 1, I think, and y minus
1 half.
1/2.
Z naught. So put x and y both equal to 0. And this.
What is the value of z naught?
2.
Z is just plotting there in function.
Yes.
Original function.
This is value of x, this is y. Put these values here,
Yes.
you will get the value of f, and that would be the value of z, because z is equal to f of x comma y. This is your z.
Z equal to.
So it would be 1/4,
2
1/4
minus 1
minus 1/2, that's 3/2. So you may simplify it. So this is the equation of a plane that is tangent to this surface that is given to you. And this is what we call the linear approximation in the case of multivariate functions. So as I claimed that we take the case of single variable and we simply extend it. Otherwise, what I would have done, I would have found these coefficients that, okay, let us take this coefficient to be a, let us take this coefficient to be b. Then after some simplifications, I would have reached, okay, the value of a should be partial f by partial x, and the value of y should be partial f by partial y. This is easy. But what I do, I take one case and I extend it. That's all. So when you know this thing, and everyone knows simply, you can extend it. So knowing this thing will lead you to this thing. Okay, we are applying the same idea to find the extreme values of a function given some interval. And we know very well that thing in the case of single variable calculus. We are going to extend the same idea in the case of multivariate, but here the idea would be a bit different and bit weird as well. Now the suggestion for you would be to take these all the formulas and write on separate pages, because formulas should be separate, so whenever we are going to appear in a test, before 1 or 2 days we should revise those all. So formulas should be written on separate pages. Then you should take any book, any calculus book, and start practicing. And if book is not good, just Google some questions on linear approximation. You will get 8 to 10 questions on any good site or Google somewhere. Just practice those. There would be answers. So this is a good practice. Otherwise, we are doing some practice here. But if you are doing an extensive practice here, this will simply waste our time. Okay, so what do you know about extreme values in the case of single variable calculus?
Critical point.
Yes,
Maximum, minimum.
maximum, minimum. So for example, I have a function which looks like this. So this is going to be the minimum value, and the function is from R to, or you can call it R star or
R plus.
R plus. But it is not necessary, because this is not the range, this is codomain set. And you have a function like this. This is going to be the maximum value. And I think we have another case. What about this?
Point of inflection.
Point of
Inflection.
inflection. So what does it mean?
Neither increasing nor decreasing.
Neither increasing nor decreasing. So can we extend this to the similar case in
3D.
in 2D or 3D? It means in multivariate functions. So we have the similar idea basically. So we have a surface that looks like this. This is going to be the
Minimum.
minimum, and similarly we have a surface. This is maximum, and we might have a surface that simply looks like this.
That's interesting.
That looks like this. So this is a surface, and simply there would be point or a line which behaves like this. This is also easy case. But there would be something else, what we call a saddle point in the case of multivariate. It happens in this case, like in one direction the function, like it's going to be the minimum value, and if you see another direction, that same point is going to be the max. It means in this direction this point is minimum, and when you go in this direction this point is maximum. So this is the fourth case in this one as well. And what we call this saddle point. Saddle is, in other words, it is called horseback. When someone does horse riding, and when we take our seat on a horse, that is exactly the shape that looks like this. This is what we call the head of or the neck of this horse. This is somehow up, and this is the back of the horse, which is somehow up, but exact position where the sit is downwards, and the sides of the horse are downwards as well. So this is the minimum point as well as the maximum point. So it has both of these properties. But how can we classify these all the things in the case of multivariate case? So let us do this way. You know very well that to find out these points, what we call critical points, the first thing is that to take the first derivative and make it equal to the zero. And then how can you decide that whether it is going to be the minimum or the maximum? You apply second derivative test. Or there are some other tests as well. Why this point is minimum? Because on the left side the function is decreasing. So on the left side the value of the first derivative is negative. And on the right side the value of first derivative is positive. Because this function is what? X squared. What is the derivative?
2x.
2x. This is going to be prime. And you know very well 2x on the left side is negative and 2x on the right side is positive. And exactly this at this point this 2x is 0. So this is called the first derivative test to determine whether it is going to be the minimum or maximum value. Or there is also the second derivative test. But second derivative test is a bit weird, that why the second derivative, which is I think greater than 0, gives you minimum and less than 0 gives you
Maximum.
maximum. Why is that the case? Most of the people don't understand this thing, but it's very simple. So if you have any question about that, we may discuss, but maybe not now.
ನೀವು ಪಾಯಿಂಟ್ ಗೆ ಕ್ಲಿಯರ್ करे छे तो सेकंड डेरिवेटिव मींस ग्रेटर देन 0 मिनिमम जो तो नहीं ग्रेटर देन 0 मैक्सिमम जो तो
You are teaching intermediate. Is it so?
यस
Actually, back करना रखा तो इसको.
I never taught.
About a chapter.
Sign. When I went to Vaudo, it was beginning of the college, and there were only students of 9th class. So they started that college 1 year back.
हाँ घट गया.
Discuss the first derivative. The first derivative here is negative. Okay. And the first derivative here is positive. Are you okay with this? And the first derivative here exactly is 0. Okay. First derivative at this point 0. On the left it is negative, on the right it is positive. So tell me what is the behavior with this first derivative changes at this point. First derivative is negative, then first derivative becomes 0, then first derivative becomes
positive.
so the first derivative increases or decreases.
Increases.
The rate of change of first derivative is
From left side.
Increases.
Increasing with decreasing rate.
no.
इंक्रीजिंग सर
The rate of change of first derivative is greater than 0. Why greater than 0? Because first derivative is first negative, then it becomes 0, then it becomes positive. So when something increases, we say that its rate of change is greater than 0. And in this case, the rate of change of first derivative is greater than 0, and you know very well this is minimum.
Yes, sir.
So rate of change of first derivative is simply the second derivative. That's greater than 0. So rate of change of first derivative is second derivative. And why this is 0? Because this point is minimum. This is simply why in the case of minimum the second derivative is greater than 0. And in the case of maximum the second derivative is less than 0. So it's very simple. But it would be a bit weird in the case of multivariate because we don't have good logic in that case. But still we can do. So we have this function and we want its critical points first. So to find out those critical points, it means critical points are what? Critical points are the candidates for your maximum or minimum or saddle point. It means critical points will be either maximum or minimum or saddle or inflection.
Yes, sir.
So these are called the candidates or the values. And how you find this? Simply set these two equations to be equal to 0. First partial with respect to x and the first partial with respect to y to be equal to 0. How many equations? Two equations. How many variables? Two variables because this function contains two variables x and y. Solve this, you will get critical points. Now how to decide whether those critical points are, let's say, maximum or minimum or something like that. So to do this we have a test what we call second derivative test. Second derivative. This is very easy, just keep these formulas in your mind, take the functions and test them. That's all. First, equate these two things to 0, find the values of x and y, then apply a second derivative test. To find out second derivative or the minimum or maximum values, the first thing is to find out the value of this del. I'm going to shorten the notation so that it would be easy for us. to remember. And what is this del? This is just find the second partial of f with respect to x, and here y, x, y, y, x. Find this determinant, and it's easy. This determinant would be fxx
minus fxy and y5.
you make just a square. Okay, this is what we call del. Now let us write some cases. F has local minimum value or just local min, in short we write, if what happens. And the second condition is f has local maximum value if what happens. These are two things first. So how to check this thing? The first thing is that the value of this del should be greater than 0, and since the value is greater than 0 in both cases, okay, if it is min, it should be greater than 0. If it is max, it should be greater than 0. But there is an extra condition as well, which we call. So I think we may repeat the same idea. What happens in the case of single variable? If it is min, this is going to be min greater than 0. Is it the case? And max less than 0. This is in the case of max and min. Just keep these a few points in your mind. What is the next condition? So the next is, I am writing over here, f has local saddle if this condition is reversed only. The function has local saddle point if the value of the del is less than 0. But you always evaluate all the things at these critical points. Evaluation is necessary because otherwise we will not be able to know what happens. And what happens in this case?
Inflation.
No, in this case the test is inconclusive. It means it can be inflection, it can be saddle, it can be min, it can be max, we don't know. In this case, inconclusive means this thing. Any of the conditions might happen, but these tests will not help us to determine what happens exactly.
So local is any ordinary.
No. Local means you got some critical points. Let's say your critical point is 0, 0, 0. It means origin in 3D case. Then it's going to be the minimum value in this small neighborhood. That's called the local min or local max. In this neighborhood. What happens beyond this, we don't know. There could be some another min value, but we are only talking about this neighborhood. So that's what we call local. And one thing is that I need to tell you that if you are given a function like this, and the function is this, x square, and this is a, this is b, and I want the extreme values, what you would do? This is going to be, origin is going to be the minimum, but you have also, you are supposed to find out the values at a and b as well, because this function is defined only from a to b. So this and this are going to be maximum values as well. Otherwise this function has no maximum, everyone knows. This goes like this. there is no maximum. But when you restrict your domain, the values at endpoints are also included in the maximum values. We don't do that usually, but it is the case. It is the case as well. Okay, ji, so are you okay with this? You can take any function like the same one, 2 minus x square minus y square, and you can find out what is going to be the min or max. But if you see, this function is very, very simple.
Where would be the location of serial point?
It would be the point that you are getting here. No? You will solve these two equations.
Right.
Those would be your candidates for critical values.
Here we are going to find extreme
Those
maximum
points, and then you decide that whether these points are min, max, saddle, or something inconclusive happens. First you do that thing. So what happens if you solve this equation? What is fx?
Minus 2.
Minus 2x 0. It implies x is
0.
0. Fy is
Minus 2y. So y implies 0.
y is 0. So the point is
0, 0.
0, 0. Okay, what do you do now? This is your critical point. What do you do now? Find this thing. That whether this thing is going to be greater than 0 or less than 0. Because it will determine that whether the point will be max min or saddle, or it's going to be inconclusive. So what is going to be
fxy.
fxx?
0.
It means differentiate this with respect to x again.
Minus 2.
Minus 2. fyy
Minus 2.
minus 2. fxy. It means differentiate this with respect to,
Y.
it is x now with respect to y, this becomes 0. Put in this one, 2,
Minus 2.
minus 2, 0, 0, this becomes minus 4, which is
Wow, minus 2 becomes plus 2.
Positive 4.
fxx is also minus 2.
minus
Both are
2.
minus 2.
Delta plus is
So plus 2, which is
positive.
greater than 0, it means this case.
Minimum.
Okay, so either this point will be
Local
a
maximum.
min or max, but not a saddle point because of this case. Now, how to determine whether it is local min or max? Just find out the fxx.
Minus 2.
What is fxx? Minus 2.
Less than 0.
You are not supposed to put any value because it's a constant, which is less than 0, so it's
Max.
local max. And the graph of this one looks like this. This is going to be the point. The point is 0, 0, and the value of the function at that point is 2. And that's going to be the
Max.
maximum value. And it's the local maximum. We may call it global as well because it is only the maximum value. Okay, so what you need to do, just
Fine.
do this thing first
Yes, sir.
and then keep these all the things in your mind. Okay, any question from this? For the entire function that is greater than that.
That's
In this case, the function goes like this. So this is going to be the maximum, and whole of the graph goes down, and it will not go down and come again like this. Then it's going to be the another maximum value, but it's going to be the only maximum. So we call it global maximum. But if we talk about the local, it means it is the maximum in the neighborhood of that point. In the small neighborhood, it's not necessary that it's going to be the very large neighborhood. It's what we call the epsilon neighborhood of a point.
Sir, correct, absolute minimum, absolute maximum, relative minimum, relative maximum. Here, point absolute maximum.
Local is
Relative.
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 It's relative to some neighborhood. We call it local. Absolute means global. So let me give you only one function and you have to decide what happens in this case. That is x square minus y square, x square plus y square minus 3x bar. Anji, what happens in this case? What are the critical points and whether that one is min, max or saddle? Should I raise this one?
Simultaneously.
Y is again 0. The critical points are 0, 0.
0, 0 only.
So just found the
This is number 1 and this is number 2. These two are somehow very interesting functions. That's why I have written these.